Hi, welcome to this module. In this module, I am going to show a demonstration of Verilog. What I am going to show is write piece of code and show how a simulator works. So, I am going to use this website called edaplayground.com to demonstrate Verilog. So, let me type that edaplayground.com. So, it loads with two windows. So, you will see on the top by default it loads with something called testbench.sv and something called design.sv. So, I am going to retain the names as it is. So, SV actually stands for system Verilog, but I will write Verilog code here as of now. So, I am not going to write system Verilog code, I will write Verilog code. So, what you have to do in this is on the right side you can type Verilog code, on the left side you write the test bench for it, which is also in Verilog. So, initially I am going to write the design part, then I will come to writing the test bench part. So, I will take it full screen. So, what do we want? We want a function called majority 3. So, we want a module called majority 3 which should give one output called out and three inputs, namely A, B and C. So, I put that description in and let us say I put end module. So, at this point I know that this is a black box which has 4 ports, right. At this point all it has is it's a black box called MAJ3 which has 4 ports. Now, I will specify what are all inputs and what are all outputs. So, at this point what I have is I have a black box and this black box has 3 inputs called A, B and C and one output called out. So, these ports, this order in which the ports are given, you should be careful about it. So, I have given output as the first one and 3 inputs, right. Later when we use this, we should know that the first one is output and the next 3 are the 3 inputs A, B and C respectively. So, I have this. So far there is no logical description, we only have a black box description of it. Now, I am going to write the internal descriptions. So, for the internal descriptions, I already said we need 3 wires and 3 gates, right. So, I will put 3 wires A, B, B, C and C, A, and I said A, B is the AND of A and B and B, C is the AND of B and C, A, C is the AND of A and C. So, we have the 3 AND gates and one OR gate which is supposed to drive the output, which will take A, B, AC and BC as inputs. So, this is the description for the majority 3 function and this is something that I have already shown. So, I have all these things. So, you can see that this website, the module, the keyword modules, input and output and so on are all shown as a purple colored thing and all the variables and other things are shown as black. You can also comment in Verilog using / and anywhere where you see a comment it is showing up as a brown colored line, right. So, this is the design description. So, what we have is we have the design under test, but we need mechanisms by which we should give inputs and we should be able to test the outputs. Let us see how to write a test bench, that is on the other panel. So, on the top you can read this, code your test bench here or browse examples. So, at this point I am not going to browse the examples, you can go and see the examples by clicking below here, you can see examples here, but I am going to write the test bench. So, the first thing I am going to do is I am going to write the test bench, I am going to call it majority 3 underscore TB and I know that test benches do not take inputs, right. So, test benches do not take inputs and they do not produce outputs. So, test bench is a black box which is completely self contained, right. The only thing we need is that we need a design under test though, right. So, the way we are going to do this is we are going to instantiate the design under test. So, what is our design called? Our design was called majority 3 and I am going to do it as a declaration majority 3 DUT1, right. And to this I am going to give inputs and do the connections. So, let us so I am going to show you a picture first. Let us see a picture. So, let us see this picture here. What we have is I am going to have a design under test right. This is going to be the design under test, and let us say this box is for my test bench. For the design, so you can, let us say you buy this chip from a shop, and let us say this bigger box here is supposed to be the breadboard, and this is the chip that you bought. You should be able to place that chip on the breadboard, right. So there will be 3 pins that will be hanging out, which are input pins, and there will be 1 pin which will hang out, which is called the output. So I am not showing power and other things, and this one I am going to call it DUT1. This is the design under test 1. We know that this chip is actually a majority 3 chip. So given 3 inputs, it will find out the majority of the 3 inputs. That is what you have in the line there. But what you can see is there are 3 lines A, B and C. So there are 3 pins hanging as A, B and C, and there is a 1 pin hanging which is out. What we need is a mechanism by which we can give inputs to A, B and C, and have a mechanism by which we can see what the output is. Right. So to do that, what I am going to do is I am going to declare 3 local things called small a, small b and small c, and I am going to declare something called out. So these 4 are going to be inside the test bench. So see that this is not part of the design under test, they are part of the test bench. I am going to have small a, small b, small c and small case out in the test bench, and what I need eventually is I want lowercase a to be connected to A, let us say, lowercase b to connect it to B, lowercase c to connect it to C, and out to be connected to out, right. So you can think of these as wires that are going into VDD, and this as a line that is connected to the oscilloscope. So you can think of this out as an oscilloscope's probe, and ABC as something that is going to your power supply, and you need 3 wires ABC and 1 wire called out to take care of this, right. So let us see how to do that. So to do that, what I am going to do is I need 3 wires A, B and C. These are, remember, wires that are local to the test bench. So these are wires that you have to connect to the power supply and whatnot, and I need a wire called out. So the one thing in Verilog is case sensitive, which means small case a is different from capital letter A and so on, right. We need to remember that, and even though these are ABC or wires, I am going to temporarily name them regs. We will see the distinction between regs and wires later. I know that it should be called regs now, I will put it right away, right. And I had this instantiation. What does this instantiation do? I currently have a circuit called majority 3. I am going to call it DUT1 under this test bench, and I am going to do this connection. So I know that the first line is output and the other 3 lines are inputs in the majority function. So you go and see the description here, right. There are, if you go and see the description, out is the first pin, A, B and C are the other 3 pins. So you want the same thing here. By accident you do not want to connect an output to a voltage supply and input to be connected to oscilloscope and so on. So what I have done is I have declared local variables here which are supposed to be connecting to VDD or ground and whatnot, and I have maintained the order in which the design is expecting the inputs and outputs. So if you have programmed in C or C++, this is like the parameters that you are passing to functions, right. This is not a function call, remember that, it is not a function call DUT1. So you have to remove your C and C++ ideas for a while. So think afresh, do not compare everything to C and C++ and ask questions about, oh, if I do this, is this a function call and so on. So assume that you do not know any programming language and you are starting fresh. This MAJ3 DUT1 is just a instantiation for DUT1. In fact, if you go and look at the design, there are 3 instantiations for AND gate. By instantiation I mean getting a physical component and placing them and wiring them. So we had 3 AND gates here, right. The same thing here, whenever you see something like this, MAJ3 stands for the circuit that we designed, it is not a primitive, remember. So we designed this is our circuit, and the name we are going to assign is DUT1, and I showed this wiring later. Small case A should be connected to capital A, small case B should be connected to capital B and so on. That will happen because that is the order in which the design is expecting the outputs. So we have those. We still do not have a mechanism by which we want to give different kinds of combinations to A and to be able to see ABC and to be able to see what the output is. So to do that I am going to do something else. So I am going to write what is called an initial block, right. So an initial block starts with the keyword initial, and then you have to put statements in it within begin and end. So this is like open and close parentheses, right. You have initial, begin and end, and within that I am going to write a piece of code which will enumerate various values of A, B and C. So this is a very simple and direct way of writing test benches. If I go and look at inputs A, B and C, they can take the values 0, 0, 0 to 1, 1, 1, or if you think of it as an integer, you can go from 0 to 7. So what I am going to do is I am going to write a for loop, right. You can see that the syntax is similar to C, except that it has begin and end and so on. So I am going to write a for loop in which I have declared a variable called I, which is an integer. It will take the value from 0 to 7, right. So if you take the integer 0 to 7, and I am going to do something which is very peculiar to a few languages. So I am going to do something like this. So I put A, B, C within parentheses, I put set brackets, and I said it is equal to I. So the interpretation of that is, you take I, which is an integer, and it is going to take values from 0 to 7. So 0 to 7 can be represented using 3 bits, right. So I, you can assume that is going to have 3 bits, and when you say set bracket ABC equals I, it will take each bit of I and assign to the corresponding bits in ABC. So let us assume that I has 3 bits, I2, I1 and I0. I2 is the most significant and I0 is the least significant. Then I2 will be assigned to A, I of 1 will be assigned to B and I of 0 will be assigned to C. So with this we are able to now see that A, B, C can actually take the inputs. So remember, if you go back to the circuit, you need to be able to connect the pins A, B and C to power supply, right. We have done something now. What we have done is we are now able to take different values of A, B and C with because I is changing. I will change, I will start with 0, 0, 0, then it will go to 0, 0, 1 and this will go to 0, 0, 2 and so on, right. And what I want to do is I also want to do this every 5 time units or so, right. So every 5 so I will give one input, after 5 time units I am going to give another input and so on. So don't ask me why it is 5, so I just picked it arbitrarily, I am putting some value there 5, right. So this takes care of the fact that I am able to change the values of ABC. This takes care of all combinations of ABC. I still need a mechanism by which I should be able to observe the values, right. So I am again going to open another block called another initial block. So there is already one initial block and there is another initial block. In this initial block I am going to write this one, right. So call a function called monitor, and I am going to say monitor the values of A, B, C and out, right. This is what I am going to do. So we have a mechanism by which we have instantiated the circuit that we wanted, and we have the statement where we can actually take the inputs, all possible combinations of inputs, and we have another statement here, another statement block here, which will monitor the outputs. So now I am going to show a sequence of steps with which we can compile, run, simulate and so on. So in the process, if we discover any errors or bugs, we will fix those things also. So the design is on the right side called design.sv, on the left side I have testbench.sv, and I am going to now simulate it. So to simulate, the first thing I am going to do is I am going to pick this particular compiler called iVerilog. So iVerilog or iCaris Verilog, I am going to pick this version 0.10.0. So I am picking that version and I am going to run. The way to run that is you go to the thing on the top, click that and press run. So when you run, you will see, so if you press run, it goes into another mode where it changes to red, and at the bottom you will see a bunch of output coming. So this is actually in the bottom of the window. So it says, so there is some something there and there is some warning. It says implicit definition of wire AC. There is some warning there, and it seems to be printing something on the screen. So let us first look at the warnings. You should not ignore any warnings that are provided. Let us go and see what the warning is. So it says implicit declaration of wire AC. Let us go and look at it. So I am using the wire called AC here, but I called this wire CA. So AC is not even declared. So this is like in any programming language, all variables should be declared. So I am going to change that first, right. So I am changing it. Now I go and run it once more, and it's not giving me any warnings. It's starting with something strange, XXXX, and then there seems to be some, it looks like it's some combination, something is happening, some bit stream is coming out, right. Let's see what that is. So this is coming out because of our test bench. Our test bench is giving the inputs, but we also wrote another piece of code which said monitor A, B, C and output. So what you are seeing is in each line you are seeing some combination of A, B, C that we tried out and the output that we got for it. So let us see this. So if A is 0, B is 0, C is 0, that will happen when I is 0, 0, A, B, C will get 0, 0, 0. So in some sense this was given as inputs to the majority 3 circuit, and the output from that comes, which is called OUT in capital letters, comes back as OUT for within the test bench, and that is getting printed out, right. So this input ABC was connected to the inputs capital A, B, C in the majority 3 circuit. There is some evaluation there, whatever the output is, that comes as capital OUT in that, and that comes back as small case OUT here, and that gets printed out. You can see that the output is, see, whenever there are 2 zeros you will see a 0, if there are 2 or more 1s you will see a 1, you can see that here. So in this case there are 2 zeros and a 1, the output is 0. In this case there are 2 1s and a 0, the output is 1, and so on. So this is actually doing our majority function. So the nice thing about that is this is equivalent to your print statements. You would do this in your C and C++ programs, right. You will go and print and see what the values are and so on. I have done the same thing here, right. So another thing that is very useful for digital circuit designers is to be able to see the waveforms, right. Sometimes the text is one way of looking at it, but picture is also a very useful thing to have, and EDA Playground has a mechanism by which we can see the waveforms. So you see the left hand side, there is open EP wave after run. So I didn't click on that earlier, but you can click on it and it will also open up the waveform. So to be able to do that, you need a few more things. So in this initial block I am going to add 2 more lines. So one line is going to say I want a waveform file, and the waveform file is going to be called dump.vcd. So this VCD stands for value change dump. So do not worry about it right now. We are saying that all the values that are there in the circuit should be dumped to the file called dump.vcd, and this $dumpVars essentially says dump all the variables. So I am going to now again run it. So when I run this, again it looks like something is happening, and now you see a new line VCD info dump file dump.vcd open for output, and then we see all these things, it comes to done. So it did not show the waveform because I did not click on this open EP wave after run. I forgot that. Let me now do that, go back and run it. Now you will see that a new window opens up here. It says use get signals button to add more signals to the waveform view. So pay attention to all the messages that you get, do not ignore the messages. So it says use get signals button. So let me see where the get signals button is. There is a get signals button here. So I am going to click on that. It shows various things here. So if you scroll down, you can see that currently there is no signal that is watched for viewing. So we cannot see any waveform yet. So I am going to click on majority 3 underscore TB. Majority 3 underscore TB has these 3 wires ABC and a wire called out, right. Similarly, if you clicked on DUT1, you will see its internal wires A, AB, AC, B, BC, C, out and so on. It is listed in alphabetical order. So what I want to see is whether the waveforms for the test as seen by the test bench. Test bench is where we actually see the output, right. Final output will be at the test bench. So I am going to pick all the signals in the test bench and say append selected, actually something changed in the back end, and I will say close. So now what we have is, we have a mechanism by which, so this I brought EP wave to the foreground. So what we see is, we see the three signals A, B and C which are given as inputs, the output is at the end, and you can notice, so let me pick this time, let us say 30, at time t equal to 30, I can see that A is 1, B is 0 and C is 1, the output is 1. At time t equal to 20, A is 0, B is, so A is 0, B is 1, and I'm sorry, so I will move it to this line, A is 0, B is 1 and C is 1, the output is 1 and so on. So you can see that in the waveform viewers, time is in the x axis, and in the y axis you see various signals, and for every signal you can see the time frame. So what are the values of different signals at different points of time, right, and you can zoom in, zoom out and so on. So you want to zoom in and see something, or you can zoom out. In this case the whole waveform fits here, so we can there is no more zooming out, we can see all of this design fit into this particular line. So it's done here. Once you are done with the waveform, in this case I know that it is correct, so I will close it. It brings me back to this window here, where I saw the design on the left side and the design on the left side, design on the right side, and test bench on the left side. So the few things that I did not talk about are, what is this initial, begin and end, what is this magic, and what is this hash 5 supposed to do. So this hash 5 is essentially saying, do this after every 5 time units. So take ABC, current value of I, assign it, keep quiet for 5 units, then go back and iterate it one more time after 5 time units, and then take the current value of I and assign it to ABC, keep quiet for 5 minutes, then come back and do this and so on. So 5 time units, not necessarily minutes. The one another thing that needs explanation is, why is this starting with a XXXX? We did not print XXXX, I did not take anything, we will talk about that in a later class. One final thing that I want you to note down is, currently if you click on this, you see that save has a star, which means the design is not saved. So to be able to save, right, you click on that save, and in this case I was already logged in, right, otherwise it will prompt you for logging in either with your Google account or with a Facebook account. I suggest that you log in with your Google account that is attached to your course. So later what we will do is, we will start seeing assignments and so on this platform. So it gives you a nice way by which you can describe the design, you can see the waveforms and so on, and this gives you a lot of practice that you can do. So eventually I intend to use this platform to show the demonstrations for the course itself. So it's good to be able to log in to this platform with your Google account, don't forget that. Later at some point of time we may even do evaluations and so on using the platform itself. So this brings me to the end of this week's lectures. So this week was quite a bit of things, we saw quite a few things. We started with combinational blobs, we saw encoders, decoders and multiplexers in a lot of detail. We also saw basically what a demultiplexer is. I want you to think about where the different things are useful, the differences between them and where each one is useful. Also remember that by changing a few things you can go from one circuit to the other. The other thing that we did was, we looked at the basic setup behind Verilog. More importantly, I exposed you to this platform. So one of the things that you can do yourself is, you can actually go and write a design which will do a 3 input XOR. Go and try and do this yourself. Write a design for 3 input XOR and modify the test bench accordingly. So it is already taking care of 3 inputs, iterating through them and so on. All you need to do is change the circuit that you want here. So you want to, whatever you call here, let us say module XOR 3, if you call that here, you have to put XOR 3 here, rest of it can remain the same. So if you feel a little more confident, I will suggest that you go and come up with your own problems and write your own test benches and so on. From next week onwards, what we will do is, we will provide more of these examples, and sometimes I will give you the test benches with which you can test your design, sometimes I will give you the designs and ask you to write the test benches for it, and later when we move towards the course, towards the middle of the course and later, we will see that you will have to write both of those maybe, right, so that you get enough practice in writing Verilog. So So, this actually brings me to the end of week 3, and I hope that this week's lectures are understandable and you are able to enjoy the lectures. So, thank you, and I will see you next Monday. Bye bye.